Okay, hello again. It is Friday afternoon. Happy Friday. Can't believe we've actually been doing online videos now for 3 weeks. But we're getting used to it, I guess. So welcome back. Today we will finish air pollution concentration models. So we'll talk about one more, we'll finish the problem we were working on, talk about one more problem, and then I've got some examples that we can work through so that you've got a few more examples. Just a few reminders in terms of homework. The modeling homework is due Monday at 11:59, so don't forget that. There's a fair number of computational problems, so try not to leave it to the very end. And there's also some conceptual types of problems. There's also the discussion board with that, so if you have questions, feel free to ask at the discussion board, and we can work together on that. Also, a reminder that the interim report is for the semester project is due April 6th. I've opened up the participation question, and that will be open through Sunday at 11:59. And then the other thing that I wanted to mention is that you should have received an email from the provost regarding grading options. The university is now moving to an optional satisfactory, no satisfactory grading system. Basically, what will happen is at the end of the semester, I will upload your grade on a regular 4-point scale. You then will have 2 weeks to view your grade. In that period of time, you will either opt in or opt out of satisfactory, no satisfactory. So basically, it's actually an opt-in. So if you do nothing, the grade stands as on the 4-point scale. If you contact and respond to the registrar, then that will be an opt-in, and you can opt in for a satisfactory, no satisfactory grade. Any questions about that? You can ask through chat, or you should be able to unmute yourself and ask a question if you do. But that's basically the way the university is going to work with the grading system for this semester. So it'll be a 4-point scale is what I will upload, and then you'll have a chance if you want to have it recorded either as a satisfactory, no satisfactory, and then transcripts will actually be annotated with a little notation that the scale was done this way to deal with COVID-19. So that's kind of all that's new right now. So if there's no questions, let's move back to the problem that we were working on. So we were looking at a situation where we're considering a stack of height 100 meters, emitting SO2 at a rate of 2 × 10⁸ micrograms per second. The wind speed, and I fixed the slides from what I had noted on the side on Wednesday, but the wind speed at the effective stack height is 3 meters per second. It is a cloudy night, and an inversion layer starts at 300 meters. And you're asked to estimate the ground level concentration at a distance downwind twice that where the reflection begins to occur from the inversion. And I'll just go back to the image that we had here. So what we are looking at is determining the concentration at this point here, 2 times x sub L. So 2 times where the plume hits this inversion layer. And as we mentioned, in this blue region here, we can assume that we have complete mixing. So we had started this problem here, wrote down some of the details, and I'm just gonna add, just note this here. just to make it a little clearer, this is 300 minus 100. It's not I don't want it to look like that it was multiplied, that L times H is multiplied by 300, but minus 100. So we calculated then that we have, we have sigma z is equal to 94 meters at x sub L. So that what we need to ask and determine now is what is x sub L? So what value, okay? We have a cloudy night. So I'm just going to go back in the notes to slide 14. So if we think through this, we said that U sub H is 3 meters per second. That means that U sub A at the end, the wind speed at the anemometer must be less than 3 meters per second. So that means that we are at the stability class E. Okay. So now we can move forward, and let's move back to our slide. Here we're going to do a little bit of moving kind of back and forth with the slides. So forgive me for this. We're back here. Okay, so we have stability class E. We then, what we want to determine is this value of x. Okay, that value of x corresponds to x sub L. Okay, since we've set sigma z as the value that occurs at x sub L. So we can use the figure on slide 16 to approximate x, or x sub L. So let's go to slide 16 here. We have a value of sigma z of 95. We're going to read across, and I'll switch to the pen. So we're going to read across here. Okay, to what do we have? We have class E, and we can read down. Okay, so that gives us, sorry. And would give us a value of around 16 kilometers. We can also use table 7.9. So we can go back here. And what did we have? We had E 95. So you can see that's about 16 kilometers. So either way, what we end up with is a value of x sub L of 16 kilometers, or we can use the table for the values for C, D, and F. So that's 94 is equal to 55.4 x to the 0.305 minus 34. And if we solve this, x is equal to 15.6 kilometers. So we have a more accurate measurement, and that is equivalent to x sub L. I'm going to add a new slide, blank slide in here just so we have a little more space. So what we want to do now is we want to find sigma y. And what we're looking for, we were asked to find the concentration at 2 times x sub L. So that's equal to 2 times 15.6 kilometers, which is equal to 31.2 kilometers. So sigma y is equal to ax to the 0.894. So again, we're going to go back to the table of our parameters for solving this equation. And that is 50.5 times 31.2 kilometers times 0.894. And that equals 1,092 meters. Okay, so these values here, let's go back and we get those from, let's get the right, from table 7.8. So slide 17. So let's just add that. So these values, table 7.8, slide 17. So that's where you'll get those values here. And now we can calculate C sub x, and that is equal to Q 2 pi to the 1/2 mu sub h sigma y L, and that is equal to 2 times 10 to the 8 micrograms per second over 2 pi to the 1/2, 3 meters per second, because we said that was the wind speed at the effective stack height, times 192 meters times 300 meters. L was the mixing height or the inversion layer, and that is equal to 81 micrograms per cubic meter. So that gives us the SO2 level. And just to kind of give you some comparison, the 1 hour standard for SO2 in the US is 75 parts per billion. And at 10 degrees C, 1 atmosphere, we'll assume it's a cold night, that would be 207 micrograms per cubic meter. So the value that we've calculated is significantly less than that 1 hour standard. So that would be a positive thing. Any questions about this problem here? Okay, if there's no questions, let's move on. So the next and the last of the models, slide 40 again, sure. So any questions about this approach? It's a lot of moving kind of back and forth. You're doing a lot of parameter estimation. As you're working some of the problems, my advice is print out, if you can, print out in a form that's easily readable, the table of the constants for calculating dispersion coefficients, print out the graph for estimating your dispersion coefficients, and then slide 14 showing the stability classes for various different conditions. That'll make it a lot easier for working the homework problems, because you're gonna need that information. As I've mentioned, all of the LUN-CAPA problems are coded. So when all of the problems are using these types of constants, so just, you can use the graphs, but this is how I've coded the problems. So let's move to the last set, or the last aspect of these dispersion models. And now what we're doing is we're looking at, for instance, we've got a highway. So we have cars going along the highway. And I actually wrote it, I guess, should have written it this way, unless you want to be in England. And we have a house. For instance, we've got some homes along this, and we've got some people. And what we want to know is you've got the steady stream of cars. So what we can do is we can estimate the cars not as a single point source, but we can estimate that as what is referred to as a line source. Or you could have agricultural burning of a field, and you want to measure the level of particulates along the edge of that field. So again, instead of modeling the fire as a single source or an area source, you can actually measure it, model it as a line source. If you go back and we think about the Meuse River Valley in Belgium, you've got numerous, or at the time they had numerous factories along that region. And instead of modeling each one of those sources individually, we could model it as a line source. So that's what we want to do. We want to go and look at how would we model this as a line source. So the equation that we use is right here. So it's a slight modification of the dispersion equation. The big difference here is that your emission rate is per unit distance along the line. So notice before we used Q. We'll switch back here. This is not equal to Q. We have this additional term right here per distance. Okay? So what we're looking at is we're modeling the rate along some distance, let's say of the highway, or some distance along a field, or some distance along this river. The other thing is that when we're using this model, if this is the distance we're looking at, so this is our distance, we're looking at this distance here, so along, and that corresponds to this length here. The wind is always perpendicular to that distance. So this model itself, there are other models that are more complicated, but this model always has the wind speed perpendicular to the distance you're looking at. So if we're thinking back at our highway, so we have cars along the highway, and we're looking at the homes, we put the homes over here. The modeling that we're doing is always perpendicular to this distance here along the highway. If the wind isn't in that direction, then the model is different, and you're not going to use this equation. But we're not going to model that in this course. That would be beyond the scope of what we will accomplish here. So let's add the slide in here so that we have some space. And I should have waited. Let's look at the problem and then we'll. So we have a situation here. This is the problem. The federal emission limit for carbon monoxide for new vehicles is 3.4 grams per mile. We're going to assume that we have 10 vehicles passing, say, our houses at 10 vehicles per second, and each of them are emitting carbon monoxide at this 3.4 grams per mile. The wind speed is 5 miles per hour or 2.2 meters per second, and we have an overcast day. And what you're asked to do is to measure the ground level carbon monoxide 100 meters from the highway. And let's also go back to this equation here. Let's also make sure we note the fact that this is at ground level. Okay, so that's the other issue here. We're looking at a person at ground level. So let's look at this problem here. So what do we have? We have an emission of 3.4 grams per mile. We have 10 vehicles passing this particular spot at vehicles per second. We have a wind speed of 2.2 meters per second. We have an overcast day. And you're asked to measure the ground level carbon monoxide level 100 meters from the highway, or 0.1 kilometers. Okay, so the first thing, we need to determine Q. So we have 10 vehicles passing per second. We have 3.4 grams per vehicle mile. We have 1 mile per 1,609 meters. So it's just a conversion. So let's see, mile cancel and vehicles cancel. So what do we have? We've got grams per mile second, which is exactly what we want. And that is equal to 0.021 grams per meter second. So now we need sigma z. We have an overcast day. So what stability class is that? Anybody want to tell me? Oh, get the right slide. Okay, so we're going to go back again. That's why I said it's really useful to print this out. So what do we have? We have 2.2 meters per second. We have a overcast day. So what do we have? Clear day. We are going to have what did we have? We had 2.2. Oh, here we go. I knew that class D should be assumed for overcast conditions, day or night. I knew that was in there somewhere. I was trying to remember where it was. Okay, so you've got overcast conditions. So we're going to use stability class D. So we have equation for sigma z. We'll go to table 7.8 back in our notes. And this is equal to 32.2. Remember, put the value in x in kilometers times 0.725 minus 1.7, and that equals 4.6 meters. Now, one of the things I want to note here is this value is quite small. Remember, we're only 100 meters away. So if you remember, okay, when we were talking about these dispersion coefficients, you're going to have a much tighter curve closer, so as x increases, closer to the source. And then as you move away, you're going to get more and more, sorry. So I'm going to draw this a little bit better. Okay. You're going to get more and more spreading out. Okay. So what happens here, this is, remember, this is your mean. This is, sorry, this is the mean, this is sigma on that side. So notice, sigma smaller. So sigma is actually going to increase as you get more and more spreading, as you move further away from your source. So C at 0.1 kilometers is equal to 2q square root of 2 pi sigma z times mu. And you're really looking at ground level, so you can use that ground level wind speed, and that is equal to 2 times 0.02 grams per second per meter. We're going to multiply this to convert to milligrams, divide by the square root of 2 pi. Sigma z, we just calculated as 4.6 meters times 2.2 meters per second. And that gives us a value of 1.7 milligrams per cubic meter. So that would be the concentration. So here's our highway, here's our house, and we're looking at 100 meters from the house. So this is the C value that we calculated would be right here. Any questions about this? I've added this slide in here. It's just various different equations. It's put in a slightly different form, but it just gives you some of the Gaussian dispersion model equations in a convenient form on one page. And it's what we talked about before. So what I thought I'd do is I've got a few example problems that we can work through. And normally I would have you work at these in groups. Since we don't have, it's a little bit harder to do that. We'll just kind of work through these. Okay. So let's look at this first problem. We'll see how many, we've got 3 problems. We'll see how many we can get through. So I'm just going to, okay. So we have, in this case, a paper mill that is proposed for a location 1.1 kilometers upwind of a residential area. So we're looking at protecting that population in this residential area. The proposal limits the emissions of hydrogen sulfide to 80 grams per second. And hydrogen sulfide has an odor threshold of 0.1 milligrams per cubic meter. Surface winds vary typically between 2 and 5 meters per second at the ends the anemometer at 10 meters elevation, and you're asked to determine the minimum stack height in order to ensure that the concentration near the edge of the residential area is no more than 10% of the odor threshold. We're going to make some assumptions to make this problem a little bit easier. Otherwise, we would have to use a much more complicated iterative approach. We'll assume that the plume rise is 0. And we will assume that the wind speed at the stack height is 60% greater than that at 10 meters elevation. So these are assumptions just to make the situation a little easier, and we'll assume that the stability class is B. So it gives us some constraints just to work through this in a reasonable time frame. Okay, so what do we have this paper mill, and it is to be located 1.1 kilometer upwind of this residential area. Q max is 80 grams per second. The hydrogen sulfide threshold is 0.1 milligrams per meter cubed. We have wind, these are surface winds, vary between 2 and 5 meters per second. What you're asked for is the maximum height. We're going to assume that delta H is equal to 0. So that means this is equivalent to H. So this is an H. So our max, our stack height. So this means that our stack height equals the effective height, because delta H is equal to 0. Okay, and we have stability class B. That's what we set it for. We can calculate sigma y, and we'll get the constants from the table 7.8. And x is given, so this is x. We can calculate sigma y. Sigma z is equal to 108 x to the 1.098, and that equals 122.1 meter. And the equation we have is C max is equal to Q. This was our maximum. Pi UH sigma y sigma x exponent minus 1/2 h squared over sigma z squared. Okay. So kind of if we just go back and look at this equation here, what we have is we have a pollutant level at ground level. We're looking at along the center line, and this is the equation we're using. And what in this case, we've set C max as equal to 10% of the threshold, so it's 0.1 milligrams per meter cubed, or 1.0 times 10 to the minus 5 grams per meter cubed. And that is equal to Q, 80 grams per second, over pi. I'm going to just put U and U sub h here. And we said that U sub h, we go back here. What did we say? To simplify the problem, we're going to assume that the wind speed at the stack height is 60% greater than at 10 meters elevation. So this, let's put this here, okay, times sigma y, which is 169.9 meters, times 122.1 meters, exponent minus 1/2 h squared, which, sorry, let's just actually h squared is what we're looking for, divided by sigma z, which is 122.1 squared. Okay, and the sigma h is equal to either 1.6 times 2 or 1.6 times 5 here. And I realized just now that I calculated this wrong. I'm gonna just do one thing. Let me, I'm gonna just, I calculated this wrong. When I fix this in my notes, okay, what I did was I multiplied by 0.6 instead of multiplied by 1.6 here. So the value is a little bit off, but it is going to be about 380 meters at 2 meters per second and about 340 meters at 5 meters per second. I'll fix this later in the notes. This is approximate because of a mistake I did when I just calculated this earlier this morning. But notice here, the low wind condition is your worst condition. So that's going to dictate the stack height. Any questions about this? Other than I apologize that, and I will add a note, obviously not in the lecture, but I'll add a note in my slides with the actual value. So, assuming no questions, let's look at this problem. It's very similar to the one we just did. So let's look at this. In this case, we have 17,000 vehicles traveling per hour on a freeway. And each car emits an average of 0.9 grams of NOx per kilometer traveled. We have winds blowing at 4.5 meters per second across the highway towards the house. And we have a developer that's purchased a strip of land along the highway, but the land is only 1 kilometer wide, and the developer is looking to maximize their profits and put homes as close to the highway as possible. So we're going to look at the worst case scenario regarding the meteorological conditions. And we're going to determine the minimum distance to ensure that NOx does not exceed 100 micrograms per cubic meter. Now, we're going to assume that NOx is conservative. We talked about that and how it's not, but in this short distance here, it's relatively reasonable to assume that NOx is conservative. So let's add a new slide. So what do we have? We have We have 1,700 vehicles per hour, each car emitting 0.9 grams of NOx per kilometer traveled. And we have a wind speed equal to 4.5 meters per second. We have land that's only 1 kilometer wide. Now the worst case scenario, we're going to assume is F, and that's because we go back and we look at this figure right here. Notice here, okay, that close to ground surface, you've got this long period of time where your pollutant concentration is highest. So we'll assume it's left, F, although you might want to go back and check it for A because we're pretty close to the highway. So it may be that this very unstable condition is actually worse. But we're going to do the calculations for condition F. And so we have C sub x is equal to 2q over 2 pi sigma z times mu. And we need to take, and I'm not going to go through the calculations, but if we take this information that's given, this gives us we've done the calculation before, and that gives us a Q value of 4.25 grams per second per kilometer. We've set C sub x as 100 micrograms per cubic meter, and we're given U, so we have 2, so this 100 micrograms per cubic meter is equal to 2 times 4.25 grams per second per kilometer, 10 to the 6 micrograms per gram, and we're just converting from micrograms to grams and from kilometers to meters, divided by the square root of 2 pi sigma z, which we don't have, times 4.5 meters per second, because we don't know the distance. Where did I get Q? Q is just as we solved it, sorry. Problem over here. So we took the vehicles per, here see, we took the vehicles per hour, or vehicles here per second, times the emission rate, and we got Q. We'll do the same thing here. We'll take the number of vehicles per hour. We need to convert to seconds. And we have kilometers traveled. So we can get, so I'll write that. We have 1,700 vehicles per hour. We have 60 minutes per hour, 60 seconds per minute. So now we have vehicles per second, and we have 0.9 NOx, and I'm just per kilometer, and I'm going to just write this there. So, kilometers traveled, and then we have 1,000 meters per kilometer. So kilometers cancel, and this was per vehicle. So vehicles cancel, and that gives us 4.25 grams per second per, sorry, this should be per, yeah, I don't need to do that conversion per kilometer. Okay. I did the conversion here. Apologize there. Okay, so this is per kilometer. And if I solve for sigma z here, that is 10.44 meters. We said we use stability class F, so this is equal to CXD plus F, or 14.35 x to 0.740 minus 0.35. And so x is equal to 0.68 kilometers. Okay, so this developer only has a kilometer wide strip along the highway, and under these conditions, each house has to be at least about 0.7 kilometers from the highway. So they're probably only going to be able to put about one row of houses along this strip. Does that make sense? Okay, we only have about 3 minutes, so we're not going to be able to get very far on this next problem. But we'll go back and I just want to walk you through this, and I will give you the answer. And then, so I'm not going to work through it. I will give you the answer, and I'm going to suggest that you try and do this problem, see if you can get the answer. I'll scan it and I'll put the answer online, but it's worth kind of just walking through this just in the last couple minutes to have you think through it. So we have a coal-fired power plant with an effective stack height of 85 meters, and it is emitting 1 gram per second of SO2 per megawatt of power delivered. So that's power out. Okay, the wind speed at 10 meters is 3.3 meters per second. We have a smooth terrain, and you're asked what is the maximum rating. So in this case, you're actually asked for the maximum rating for the plant if the ground level SO2 cannot exceed 170 micrograms per cubic meter. Okay. The first thing, and I'm going to just work through, and I'm not going to do the calculations, but what I wanted you to do is kind of work through the process of solving this problem. Okay. So the first thing you need to do is figure out what is the worst case. So you'll need to look at the wind speed, and you'll need to think through, okay, what would be the worst case. So think about what the plumes would look like under various different conditions, and where would you see, under what conditions would you see the highest concentration. So then you need to determine P. Okay, so once you figure that, don't forget this is for smooth conditions. So you need to multiply by 0.6. You're going to need to determine the wind speed at the stack height. So and then what you will need to do is to determine this value for Cu over Q max. And if there's both an equation for this and a graph, and you can use either one. Line cap is always calculated with the equation. And then lastly, you've got Q. And this is what you're going to determine. You're going to determine Q. And remember that what you're given is that you've got 1 gram per second SO2 per megawatt out. So you're going to determine a Q value, and then based on this, you can determine the megawatt delivered in the plant. Okay. So I'm going to give you the value. It's actually 32.4 megawatts. And I'm going to suggest that on your own, you work through that. You might want to try and consider different stability classes. You could try stability class B, see what it is. Try stability class E and see what it is. Okay. See what you're going to determine for the limit in terms of the output of this plan. So I'll end there unless anyone has any questions. No questions? So have a good weekend. Don't forget the homework is due on Monday. There's quite a few problems. So my advice is make sure you spend some time on the weekend doing it. And I will post the solution for this later today sometime after I've posted the lecture. And the recording will also be on YouTube and on D2L as usual. So have a great weekend and